Welcome back. So we will now that we have understanding of determinants, we will look at how to use these determinants and solve our linear equations. Okay. So linear equations, we already have understood that they are nothing but a vector matrix dot product multiplication or multiplication or dot product essentially. uh, and we will see how determinants are used in order to determine whether a set of linear equations has a solution or not. Now let's consider these two equations itself. Minus x1 plus 3x2 equals to 7, 3x1 plus 2x2 equals to 1. There are multiple ways to solve the linear equations. Okay, one is substitution method. Okay, I can write that here. One is okay, substitution method. Another one is elimination method. Another one is Gauss Jordan elimination method. Okay, another one is Kramer's rule. All four are easy if you understand. um, okay, so four methods to solve the linear equation. Now a system of linear equation that has no unique solution, okay, or it has multiple solutions, in other words. Okay, so that is said to be non-singular linear system. Okay, and singular linear system is where it has one unique solution. We will see that how to do. Okay, so I'm going to take these same equations here. um, okay, so let me take these same equations here. Minus x1 plus 3x2 equals to 7. Okay, minus x1 plus 3 x2 equals to 7. So instead of x1 and x2, I'm gonna replace those with x and y for easier understanding. Okay, and likewise I will take 3x1, 2x2, 1, 3x1, 2x2 equals to 1, 3 to 1, right? 3 to 1. Yeah. So if we solve these set of linear equations, okay, first we will look at the substitution method. Okay, the solution we have already obtained. So the solution is minus 1 comma 2, y equals to 2. This, using substitution method, what you can do is, if you ask I mean if I ask you to solve it using your intuition, this is how you would do it generally. So what you would do is, you will just solve for x first. You'll convert this entire statement into x equals to minus 7 plus 3y. Then this value you will substitute in the second equation, and that way you will have only y values, and you will get y value, and then you will again substitute this y value in the original equation, you will get x value. Okay, now once you have, what it means to have solution of linear equation is nothing but the intersection point. A set of linear equations can have unique solution if and only if their determinant is non-zero and they intersect each other at certain point. The point of intersection is nothing but the solution of those linear equations. Okay, so this we can see programmatically also. Programmatically it's very easy. I've taken the same vector, or the combination of vectors is nothing but matrix. I've taken the matrix, I have taken the vector here as separate values. I'm printing the shape, you can see the shape as well. 2 rows, 2 columns, 2 rows here. Okay, and I can immediately calculate the determinant. Determinant turns out to be minus 11, which is non-zero. If it is non-zero, then we say the set of linear equations have only one solution. So for us it is easy to calculate programmatically. All you have to do is use numpy's linear algebra dot solve function and pass the matrix and the vector. You'll get the solution minus 1 comma 2. Okay, if you want to visualize it, you will get this something like this, a plot something like this, which is what it is shown here. Okay, so this is how you can do it programmatically, but just simply by calling linear algebra dot solve, and substitution method you can do like this. Let's look at elimination method also. Now in elimination method, since you have minus x here, you are essentially trying to get rid of this x term. That way you will have y term, you will get the y value, and substitute back into the original equation, you will get the x value. So what you can do is you can multiply this first equation using a scalar 3. Okay, what happens when you multiply a vector with a scalar? It gets stretched. Okay, this we have seen in the previous class as well. It stays in the same direction but gets stressed because you're multiplying with positive value, stays in the same direction. Okay, but the mathematically when you try to add these equations, they get cancelled. You get y value equals to 22, and finally y value, sorry, 11y equals to 22, y value equals to 2. Now put this value in the first equation, you will get minus 1. Okay, again visually they look the same thing, they are intersecting with each other at point minus 1 comma 2. Okay, so then we say this set of linear equations has unique solution. Let's look at Gaussian elimination as well. Now for Gaussian elimination, what you do is you take the vectors. Okay, here you can do a Gaussian elimination. Okay, so you take the let me open another tool where you can see the steps um, along with the complete steps. Okay, yeah. Okay, so first take 2 by 2 matrix. Okay, you take the matrix value as here minus 1 3. Okay, so this value should be um, minus 1 3, and the other one is 3 2 3 comma 2. Okay, I think this is not taking the, oh yeah, so this is the one, this is the tool I was looking for Gaussian elimination. Okay, um, you can supply the steps. I think one moment, let me check the get the tool. Okay, the tool is here. It was here only. Okay, Gaussian elimination. Let's set the matrix dimensions. So it's a, let's assume it's a, we are going to use only 2 by 2 matrix. Okay, 2 by 2 matrix, but we have to also supply b values. So that is why you have. So the values are minus 1 comma 3 and equals to 7, and the second one was 3 2 1. Okay, 3 2 1, and when you try to solve it, you can see each and every step performed. So the Gaussian elimination method is mostly the non-diagonal elements that are there have to be made as 0. You're trying to make these non-diagonal elements as 0. By doing that, you will be easily solving the values. So the way how you do is all the, again remember in Gauss Jordan elimination you are only going to do the operations on rows. Okay, So in this row, if you notice, you are inverting the sign, you are multiplying with -1. So you get from -137, it became 137, and then in the next step you are eliminating the first column by subtracting. Okay, actually there is one more step missing here. You have to also divide by, sorry, multiply by 3 and multiply by 3 to the first one and then subtract. Only then you will get 0. When you multiply by 3, there is one more step missing here. Okay, so if you multiply by 3, this becomes 3, and this becomes -9, this becomes -21. Okay, this becomes -21. Then this is 3, right? 3 minus 3 becomes 0. Minus 3, um, so -3 into 3 is -9. -9 of -2, sorry, 2 minus of -9, you're trying to subtract first row from second row. Okay, either way. So 2 minus of -9 will become plus 11. Likewise, 1 minus of -21 will become plus 22. So that is how you have got this here. And upon doing this, the next step is to eliminate this term. Now you eliminate this term by dividing the second row by 11. Okay, so when you divide by this 11, you will get 1 here, and after that you can eliminate the second column by again further eliminating this -3 by subtracting, basically. Once you do that, you finally you will get this value, and this x1 is directly equal to b. No, directly x1 value is -1, directly x2 value is again 2. So that is what you have here. This is Gauss-Jordan elimination. You have to do a lot of steps in this method. Next, look at Cramer's rule. I was going to talk about Cramer's rule anyway. Here, let me brief it out. So what you do is, this is very intuitive method, very easy method. First, you calculate the determinant of original matrix. In this case, -1, 3, 2, 3, 2. For this matrix M, you calculate the determinant. What is determinant? Determinant is nothing but -1 AD AD minus BC. -1 into 2 is -2. Minus of 3 into 3 is 9. So it becomes 11. So D becomes, determinant becomes 11, -11. Now what you do is, you replace the first column with 7, 1, which is this. Okay, and then calculate the determinant. You will get 11. Likewise, you replace this y column with 7, 1 and calculate the determinant. You will get -22. Finally, once you have determinants of all these three, okay, you start dividing. To get x value, divide the determinant of x divided by whole D, determinant of original matrix. Then you will get -1. Again, determinant of y divided by determinant of D, you will get +2. So that way again the plot remains the same, because it intersects at this point. Okay, but for programmatically it is easy. So these are all 4 different ways to solve, but programmatically we don't care. We just simply call this solve method on top of this, and you will get the values -1, 2. To visualize it, you can also, again, we know how to plot it from the previous sections. We will simply plot it. Okay, so this, we can see this set of linear equation has only one unique solution. You can tell that just by looking at the determinant value. If the determinant value is non-zero, then this set of linear equations has one unique solution. Also, if these lines intersect with each other, then they have unique solution. Okay, I hope this is clear. Next, let's look at when would this set of linear equations have no solutions. Okay, very simple. These set of linear equations have no solutions when their determinant becomes 0, or when x and y value are infinitely large. Essentially, if you notice this value, we have calculated, we have taken these equations. I'm only going to change the second equation. Okay, and I have taken these values here. and you have calculated the determinant, it is same as this one. E to the power minus 16 means there are 16 zeros before 499. Okay, so which is approximately equal to 0. If the determinant is 0, then a system of linear equation have no solution. Now what does that mean? So here one solution means they are intersecting. What does no solution mean? That we will see. Okay, let's look at again, go back to the same set of linear equations. Let's modify the second value, 3 minus 9 1. Okay, we will modify this value with 3 minus 9 minus 9y and 1. So if you again calculate, it doesn't matter what method you use, you notice there is no solution. If you try to calculate substitute, and you will obtain, somehow you will obtain one linear equation will get cancelled. Okay, and sorry, so you will get no solution. And if you notice, both these two lines are parallel each other, that means they have no solution, they never meet. Only if they meet, they have one unique solution. Okay, if they don't meet, they don't have any solution. This can be picturized by plotting. If we plot it, we'll get these values. They are parallel to each other, they never meet. So because they never meet, they don't have any solution. And if you try to calculate the data points, you see they are infinitely larger, e to the power of 17. Okay, so it's a huge x value, huge y value. This y value is 17 and 16 because my CPU has that limitation. If you use a supercomputer, this value may come to some 100 or 200 or whatever. If you use much bigger computer, you will get even bigger value. So that way they are never going to end, they are never going to meet. Okay, they are always parallel. So that is why we say a system of linear equations has no solution. Let's look at another example wherein which we'll make minor modification. Instead of 1, we'll use minus 21. Here we are gonna use minus 21, and we will see what it means to have, okay, multiple solutions. So when you try, irrespective of what method you try to solve again, so you notice that one of the equation gets cancelled. Okay, and if you pay attention here, if you notice, one is a multiple of the other. 7 3s are 7 minus 3 is a 21. 3 minus 3 is a minus 9. Minus 1 into minus 3 is plus 3. When you have such multiples, then we try to calculate the determinant, which is extremely small or negligently 0. Or when you try to solve the equation, the values are very small. This is 0, this is almost 0, e to the power of 0 is 0. Okay, and this, if you notice, e to the power of minus 16 is extremely low, very small. Okay, um, so what it means for an equation to have infinite solution? It means one of the equation is coinciding with the other one. So 3, it's as same as multiplying a scalar value to this original one, which is minus 3, which means you are stretching the second vector over first vector. Okay, so that's why okay, let's look at here interactively, let's understand what it means. Okay, so if you multiply, you can see the values, see x and y values are changing. So that means the infinite number of x and y values are present for both the equations. Okay, that is what it means. So when two equations coincide with each other, okay, then the system of linear equations has infinitely large number of solutions. Next, let's look at Kramer's rule. This we already saw in the linear equation, again just repeating it. So basically for Kramer's rule, you have to calculate the determinant of the original equation, and then replace this first column with the values of minus 3, 10, minus 4, and then calculate determinant, which is what we have done. We have replaced this first column with minus 3, 10, minus 4, and it looks like this: minus 3, 10, 4 after replacement. And then we have calculated the determinant x, likewise determinant y, for after replacing the second column, minus 10, 3, 10, minus 4, again minus 3, 10, minus 4. Once you calculate, finally you will get the three equations that meet at certain point, although we don't have a 3D plot here to visualize that, but they meet at three different points. So hence we say, using Kramer's rule, this set of linear equations has one unique solution, okay, in xyz plane. Okay, so that is what it is. If you have understood using these linear equations, solving these linear equations by using determinants and various methods, then we are good. Now why do we even solve these linear equations? Very simple, because we want to understand, we want to find out this why. No, we want to find out, we want to predict y in future. That's why we want to solve, convert these linear equations into matrices, and we do various calculation determinants, or we directly try to solve them. Okay, so hope this is clear. If this is clear, we can end the class.